All right. So for the final talk of today's slate of talks, we have Fabiola Manjarrez-Gutiérrez telling us about bounds on the handle number of sutured manifolds.
Well, I'm very happy to be here, and thank you, Ken, for organizing this nice workshop. And well, this work is joined with Ken. And well, let me show you this diagram. This is like this summarizes what we talked about. So for knots, we have this concept of Tonnen number and Morse number. And so the idea is to move these concepts to sutured manifolds. And so for this invariance of knots, I have enough proof that there is a relation between these numbers. So the Morse number of I is bounded by its Tonnen number. So now our theorems generalize this bound for sutured manifolds, and also provides a lower bound between these two concepts. Well, all these symbols correspond to what we call the linear handle number, that will correspond to the idea of Tonnen number for a knot, and this will denote the circular handle number of a sutured manifold that will correspond to the Morse number. So, so let me tell you, just remind you what this Tonnen number means. So recall that for a knot in a string, a Tonnen system is a collection of arcs properly embedded in the exterior of the knot, such that when we take the exterior of the knot union this Tonnen system, we got a handle point. So the Tonnen number is the minimum cardinality of all the Tonnen system and this Tonnen system corresponds to a linear handle decomposition of the knot exterior. So that is given by so we can fill the knot exterior by adding a handle, set of handles, then a collection of two handles, and finally one handle. And so then we can count this number of handles. The number of handles will be the cardinality of the Tonnen system. The number of two handles is the cardinality of the Tonnen system plus one, and we just need a handle. And so the total number is by the cardinality of the Tonnen system plus 2. And if this realizes the Tonnen number, so this is just 2 times the Tonnen number plus 2. Okay. So what is the Morse number of the knot? So we can take the exterior of the knot and a cipher surface for the knot, and well, ask if we can fill out the exterior of the knot using this cipher surface. So of course, if we have a fiber knot, we can do this using the vibration of the knot. In this case, we say that the Morse number is 0. But for fiber knots, the Morse number is 0. So if in the case that we have a non-fiber knot, so we have a cipher surface, so we cannot fiber the exterior of the knot with a cipher surface. So we need to add 1 handles and 2 handles to the exterior. So we start with this cipher surface, we fill it up, and then we add a bunch of 1 handles until we cannot add anymore. And we got this until this will give us another cipher surface And then we need to add something else. That's something that we need to handle until we go back to our cipher surface. So the handle number of a cipher surface will be the minimum number of handle numbers needed to do this, and the Morse Markov number of the knot is well, the minimum handle number over all its possible cipher surfaces. Okay. And this corresponds to what is called a circular handle decomposition of the knot based on a cipher surface. So, okay. So then I think that in 2010 he proved the inequality I mentioned, that the Morse Markov number is overordered by twice the total number of the length of the knot. And so he did what he did, he gave a Morse function, a linear Morse function, realizing the total number of the knot. And then he constructed a circular Morse function, with realizing with the exact number of critical points given by the linear Morse function. And so he did like, he changed the gradient and what would forms and those. Okay, so in this picture we can see the two of the composition I just described. And so the question we asked is if we can, well, indeed this question was asked by Pagino, if what was the geometrical relation between these two decompositions. That means that if we start with one of these decompositions, how can we get a linear decomposition or the other way around? So to do so, we work with Sutured manifolds that they were mentioned yesterday in a couple of talks. But let me remind you what they are. So we start with a compact oriented tree manifold, and a suture structure for that manifold consists of a disjunct pair of surfaces, R plus and R minus, the boundary of the surface. And so that R plus is well, the orientation of this piece of the boundary of the manifold is consistent with the orientation of the inherent orientation of the boundary of the manifold whereby the manifold, and R minus is the orientation in reverse. When we remove those collection of surfaces from the boundary of M, we are left with a collection of annuli and tori. Moreover, we require that this collection of annuli joins the boundary of R plus and R minus. And so we are going to be using this notation for a Sutured manifold. And here we can see simple examples of Sutured manifolds. Those are for our paper. And well, here we can see other examples of Sutured manifolds. And well, these pictures are of MSAT, and they are in our paper. So, well, we are going to define this number B for a Sutured manifold to be 0, 1, or 2, depending on whether neither just one or both of R plus or R minus are. So So we'll be working also with decomposing surfaces for suture manifolds, and we'll just record what it means. Is an oriented, properly embedded surface, which intersects the toroidal sutures in horizontally oriented parallel essential centers, and each annular suture, the boundary of the composite surface intersects the annular sutures in either in circles parallel to the core of the annulus or essential axis. And once we have a decomposing surface, we can remove a regular neighborhood of the surface, where we can chop the manifold M along each surface S, and the obtained manifold inherits a suture structure. Okay. Okay, I'm not giving the precise description of the inherent suture structure, but in this picture you can see what it means. And we denote this operation by this symbol, and we say that the M prime gamma prime manifold is obtained from a suture manifold decomposition. Okay, so Jennifer already talked a lot about compression, handle bodies and compression bodies. So I'm gonna repeat the definition, but with this, looking at them as suture manifolds. Okay. So, and this also allows more general compression. So we'll start with R minus, a compact manifold. So we allow that, a compact surface. So we allow that surface to have boundary. And so we construct the compression body C, taking the surface, the compact surface across the interval, and perhaps a union of 0 handles, and then we add a bunch of 1 handles. And so that will be our compression body. And so the compression body has a suture structure given by the following. So R minus is will be just the minus copy of the surface R minus. Gamma is the boundary of gamma is boundary across the interval, and R plus is what remains of the compression body. So here you can see this real picture of a compression body, and here the schematic picture. And so we can also do this construction in the dual way, just by swapping R plus and R minus. And so instead of adding, I'm doing the dual construction, adding 0 and 1 handles, we add 2 and 3 handles. Okay, so we have, so this construction will be called a compression body, and this one a dualized compression body. So this definition includes the standard compression bodies and handle bodies. Okay, so now we are going to define what is a linear Heegaard splitting for a suture manifold. In this case, this definition is for suture manifolds without toroidal sutures. So a linear Heegaard splitting is denoted by MS or ADX. It's a decomposition of the manifold into a compression body A and a dualized compression body B. So another definition is the handle number of the compression body. So this is, we just count the handles needed to construct and minimize the handles needed to construct this compression. Okay. So again, so this is the definition of a linear Heegaard splitting. And so we have this compression body and this dualized compression body that are glue along the surfaces. And the handle number of a Heegaard splitting, linear Heegaard splitting, is just counting the handle numbers of A and B. And the handle number of the sutured manifold is given by minimizing the handle number of the over all possible Heegaard splitting. Well, just one observation here that this when this is the Heegaard surface. So the Heegaard surface is a decomposed surface. Well, now, so the definition of a Heegaard, circular Heegaard decomposition. So now we have a sutured manifold, and well, possible it can have sutured toroidal sutures. So now we are going to take two disjoint properly embedded surfaces F and S in the sutured manifold, and with these conditions. The surface F is a decomposing surface of the manifold. And the sutured manifold decomposition of M along F yields a sutured manifold without toroidal sutures. And the last condition is that the second surface we take is a Heegaard surface for the sutured manifold decomposition. Okay. So we are just like decomposing along F, and what we obtain, we find a linear Heegaard. So we say that a second homology class is regular if any surface representing that class meets each toroidal. Well, this is just an observation that if the sutured manifold doesn't have toroidal sutures, then every class is
and if can have many boundary components in the same torus?
It can have many.
Many boundary components.
They just need to all be parallel.
Or parallel at the same orientation.
Yes.
So be a decomposing surface.
It's a decomposing. Yeah. So this surface also really disconnected. So the handle number of a circular Heegaard splitting is just again counting the handles of the handle bodies. So the handle number of a sutured manifold and a decomposing surface, well, we just minimize over the handle numbers among all Heegaard splitting of the decomposed sutured manifold along F. And then, given a regular class, we can define the handle number of of the sutured manifold and the class to be just the handle number of when minimizing the handle number of M, F, where F represents the second homology class. Well, we say that a a surface representing the second homology class realizes the handle number if, well, if there is a surface, a Heegaard surface, so that this Heegaard splitting attains this. Okay, so the zero regular class, sorry, the zero class is a regular class in the case that the suture manifold doesn't have the sutures, and so so in this case, this handle number is also contained in this definition. Okay, so here are some technical results to prove for the two bounds. Our result. So well, we say that a decomposing surface in a suture manifold is conditional if, well, if this happens. All the arcs of the boundary of F in any component of an angular suture are coordinately oriented, and no empty collection of simple clusters of this intersection is trivial in the first homology group. So if that happens, the surface is said to be conditional, and it is well conditioned if the above, if the two conditions above holds, and if in addition no empty subcollection of these components is not homologous in the second homology. And well, a Heegaard splitting of a suture manifold is conditional or well conditioned if F is conditional or well conditioned. So one of the things we prove is that for a suture manifold that we can always find a well conditioned Heegaard splitting realizing the handle number. And well, as we consider also one of the technical results that are very useful is that, well, given a connected compression body with handle number C and a conditioned surface for that compression body, we can always find a conditioned surface, so that after decomposing that compression body along that surface, we obtain again a compression body. And we can count the handle numbers of the new compression body, and they have the same handle number if the minus part of C is not empty, and well, we have to subtract to indicate that C is a handle. So we need, well, we need these results. Well, another thing that may happen is that there may be suture manifolds for which, a suture manifold with boundary tori and okay, so for which all boundary tori are toroidal sutures, and probably a non-zero second homology class may fail to be regular. For instance, some link stereos with linking number 0. This is what can happen for those. But we can restructure the suture structure to avoid that thing. And the way we do it is just we choose all the boundary tori to belong either to S plus or S minus. So this change of the suture structure instead of the handle number. So in the statement says that given the same manifold with two different suture structures, which agree everywhere except for them. So this one may have chloride components, and this just have annular components with sutures. So if this condition happens, then the handle number is present. Okay. So that would let us work with, well, state our theorems just for suture manifolds without chloride sutures. Okay. So the first, so this is the upper bound statement, and it says that, well, given a suture manifold without chloride sutures, then for any non-zero second homology class, we can find a surface that represents that homology class, so that the Heegaard splitting MFS has this handle number. And so consequently, we find this upper bound for the handle number of that homology class. Well, recall that this number D may be 0, 1, or 2, depending on our plus or minus are. Well, what it says here, either just one or both. Okay, so let me sketch and prove the proof of this theorem. So, okay, so we start with a linear Heegaard splitting, and so we want to construct a circular Heegaard. So in this here, you can, well, this green surface, sigma, is the surface for a linear Heegaard splitting. So it splits the suture manifold into the compression body A and the dual compression body B. Okay. Well, by the previous results I mentioned, we know that there is a conditioned surface that realizes the circular. But given a second homology class, there is a conditioned surface that realizes the handle. Okay, well, and it's transversal to the Heegaard surface. Okay, so further we can find a conditioned surface F that is homologous to F0, such that the restriction of this surface F, so this picture you can see it. So this is the restriction of the new conditioned surface homologous to F0, so that this surface restricted to the compression bodies A and B, decompose those compression bodies into compression bodies, also by the results I mentioned. So the decomposition of these A and B is denoted by A prime and B prime, and also we can count the handle numbers of these A prime and B prime compression bodies, and it's just well, either we have the same handle number, or we have the original one. Okay. So we have this settings. So recall that we want to find a circular Heegaard splitting. That is, so given this decomposing surface, we want to find, or we want to cut along this surface and find a Heegaard surface for the pieces. So such Heegaard surface is going to be just the transverse sum of the Heegaards of the linear Heegaards of the sigma and the conditional surface that we have. So we cut along, we decompose the manifold in gamma along F, so we get this decomposing this n gamma prime. And well, the claim is that this surface S is a Heegaard surface for the decomposed sutured manifold. So why is that true? So we find this this surface S decomposes when we cut along the surface S, we got this pieces A prime bar and B prime bar, and these are just very close to the above one, just by adding this tiny product. So when we count the handle numbers, well, these are compression bodies. So when we count the handle numbers of these compression bodies, because we just add a product, so they have the same handle number as the A prime and B prime compression bodies. And well, by the counting of these compression bodies, we find this. And so we have found circular Heegaard splitting with the handle number we get. So the lower bound. Now we are going to start with a circular Heegaard splitting, realizing the circular handle number, and we want to construct a linear Heegaard splitting. So well, this is in such a way that we have this inequality. So observe that in the previous one we just had in the previous upper bound, these three numbers were the ones that were interacting, and in this lower bound there is this new thing. And so this is defined, well, this number here is called the handle number characteristic of the second moduli class, and it is a kind of Euler characteristic. So here is the definition. So we minimize over the surfaces that, well, we minimize this number over the surfaces that represent the second moduli class. Well, so that this surface, which represents this surface F, realizes the handle number, and we count this now. So this is just the Euler characteristic of the surface. And so this is, so given, let me tell you, that once we have a sutured manifold and we have a decomposed surface, okay, that surface inherits a handle structure. Okay, so this number here denotes the zero two-dimensional handle for F, and this denotes the two-dimensional handle for the surface F. And well, since the surface is a decomposing surface, and we are in a sutured manifold without sutures, so this surface, every time it crosses the annular sutures in arcs, those count this. So this refers to that, to those arcs. this is the proof of this upper bound. So let me go through each of the pictures here. So we start with our suture manifold, and so this is. So I just want to tell you one place of this group. So we take our suture manifold, and we have this decomposing surface, and that realizes the handle number. So we are assuming that the boundary of F is not contained in the annular suture. Okay, so here we see colors of the decomposing surface. So this picture represents the manifold decomposition. Here now we see the Heegaard surface for the decomposed manifold along F. We can also see the compression bodies and the cores of the 100s and the 200s. Okay, so in this picture, we have added so what we are going to do next is to add to the compression body B, this half of the collar, and to the compression body A, we have to add this other, because we want to reassemble F. So here we see that. So we have added half of the colors of F to A and B. And also we have this color of R minus and the color of R plus. And so we remove the color, we remove this color from A and B, and so this is well, this A bar is just A, the previous compression body, union the half of the color of F, and removing the color of R plus, and similarly we have this B bar. And to A bar we add the color of C minus, and to B bar we add the color of R plus. So one observation here is that when we add the half colors of F to each A and B, so the handle structure that F inherits from the suture manifold, when we take the half colors, that handle structure becomes, well, all those two-dimensional handles become three-dimensional handles. And now we have to include those handles into these things, A bar union the colors. Okay, so
quick question. So why helping? Why only what? Can you add just the full product structure to just one side? So why helping? Just one. Well, maybe this is coming up later on, but I mean, so why are you doing the process in 2 steps? Does that have to do with some interaction between the handles? Or? Well, just wondering. I mean, it's,
yeah, so well, I think on one hand it gave a cleaner way of describing it, because
so just
you know when you're thickening up the surface, you've got this handle structure of the surface, and when you thicken up the 2 handles up to 3 handles, you kind of have to kind of choose. You know, are your one handles going to be, or your 2-dimensional one handle is going to be 1-dimensional 3 handles or 2-dimensional 3 handles. You know, that's going to depend on which way you're attaching them. And splitting it up into those 2 sides, first of all, just kind of allows us to kind of keep it somewhat balanced to keep track. But
there's a balancing act.
There is a little bit of the balancing act. But, you know, I mean, yeah.
Because of the difference between that and one.
And then especially when, say, some component of F doesn't, say, meet R minus, then you're going to have a 0 handle for that from one view. So you would then have to be careful about saying, you know, being a little bit more careful with noting, taking into account all the different components and treating them differently. And I think, I mean, maybe you could make, I mean, we're not claiming this is the sharpest bound we're going to get. I think we're claiming this is a bound you get. And an effort of kind of making it a cleaner statement. I think we had discussed this issue at some point. But it was kind of cleanest to go ahead and keep it, not have to kind of address all the different types of pieces of F. Yeah. And I feel like there might be yet another issue that came up. So maybe that's all. No, that's a good question. I have to remind myself what the right answer is to that, but I think it was in part of just getting a cleaner answer.
Well, so let me see what I say. Binary steps. So, so we just okay. So here we're just adding the so this denotes the 0-dimensional handles F, and then what we added to this Heegaard using the polar of R minus, but we but up to here this might not be a compression body, but after we remove the 2 handles of F across this half of the polar F, we obtain this is a compression body. And for B, we do the dual software. So these things are compression bodies. And And so this, here you can see that the A bar, A star, sorry, is a, well, it's a compression body for which the minus, R minus of this compression body is R minus of the supermanifold, and the R plus R of D star is the R plus R of the manifold. And I think there's something else we have to do. Yes. So here we have this compression body, but for this to be a linear Heegaard splitting of the suture manifold, well, we need to have these handles all attached to R minus cross R. So the last step is to pull the fields of the 100s of A star. Well, they have to be, and the 100s of B star to be to put on R plus. So this will be a Heegaard splitting for M, a linear Heegaard splitting, and after we compute the handle number, well, this is a summarized computation, but we find that this Heegaard splitting, the construct, has exactly this number of handles, and that gives the upper bound. So this is the summarizing both bounds. So let me go. Well, I don't know.
So just to go back to Lucy's question, I mean, I think in the end, the point was to make sure that we had a Heegaard surface.
Yes.
That's why we had to take both sides. If you only added handles from the other, then you're going to get an imbalanced. You know, the boundary minus of the B and the boundary plus of the A won't have the same genus.
So use a balancing.
It is a balancing act.
Okay. So this is there. So let me go back to the case of Lee's chemistry. So we consider the exterior of the link, and well, and we consider it as a suture manifold by saying that all the toroidal components belongs to R plus. So with this suture structure, we observe that the linear handle number is just well. So we don't have toroidal suture, so this is just the same definition. So this is for the zero class. This becomes twice the total number of I plus 2, and this one is just the Morse of the cost number. And also in this case, D is equal to 1 because R minus is empty. And also this the suture, I don't recall the suture character, but whatever. This amount here is just twice, well, the Morse Novikov genus of R, where the Morse Novikov genus is the genus, well, is the genus of a surface that realizes both the handle number and this thing. So just plugging in everything into this in these inequalities, we obtain this. And well, we recovered that enough. And so the question, one of the questions is that if the Morse Novikov genus is the genus of the genus is the minimum
So is there an inequality between those two genera? Is there always an inequality between the two? Is the genus of the link always less than?
Oh, yes. So this is the minimum, this is the size.
This is the lower
minimum,
bound.
the lower. So there is always known that this is going to be greater for the Morse Novikov genus.
Yeah, the Morse
is-
Novikov genus
is
is realized by an incompressible second surface.
Ah,
The question is,
it
can it be
minimum.
realized by a minimum genus
Mhm.
second surface?
yes,
So you're saying F has to be incompressible?
yes.
Yeah, we can show that F has to be incompressible. Like there's some. So here's the paper I did. We showed that was in true for knots, but the proof basically extends to links.
So that
But so yeah, the same argument basically works for links. So then it's just a question, can we assume that such a surface is taut?
So it's just that I'm not so sure about the numbers, but how do you get a surface F that realizes both the Handel number and the Euler characteristic of the class? I mean, simultaneously.
I mean,
Why is that possible? It's just that I forgot.
it's just kind of from the definition of the sutured characteristic. So you can easily make surfaces that realize the Handel number with much bigger sutured characteristic. There are ways of.
To realize the Euler, you need to already have realized.
the Handel number.
It's
Yes.
part of the definition.
Okay.
Mhm.
Yeah, that's what I meant.
Yeah.
Let's check.
Well, so finally, so given a sutured manifold, so for any integral regular class, well, we define this function. H of the class used to be the Handel number. So we have this function that have these properties. So for any two regular classes, this number is bounded as a constant depending on the suture structure. We also have this equality for any integer, and also this other inequality for m large enough. So, and these three facts will follow from our results from the thing. Well, I'm not going to mention this theorem, and well, we also can extend this function. Sorry, it's missing. And so this function satisfies this condition. Right, and that's it.